Agronomy and Horticulture Study Program has a total 71 academic staff members graduated from reputable universities all over the world. Agronomy and Horticulture Study Program offer you excellent facilities. We have 11 classrooms, library, executive lounge, toilet in each level, and praying room. For accumulated study and research process, we have 26 laboratories, including molecular biology laboratory, plant breeding laboratory, testing laboratory, ecotoxicology and bioagent laboratory, post-harvest and biomass laboratory, tissue culture laboratory, seed testing and storage laboratory, microtechnic laboratory, and 70-hectare experimental fields, including Lewi Kopo and Cikarawang Experimental Field for lowland research, Sawah Baru Experimental Field for paddy research, Cikabayan Experimental Field for plantation research, Jonggol Teaching Farm for palm oil research, Sukamantri Teaching Farm for fruits research, and Pasir Sarongge Experimental Field for highland research.
The Agronomy and Horticulture Study Program always prioritizes safety in all activities. Personal protective equipment, clothing for practicum when applying pesticides in the garden, and a shower laboratory are some of the safety facilities for the Agronomy and Horticulture Study Program. To anticipate a fire, the Agronomy and Horticulture Study Program has been prepared smoke detector, alarm, and evacuation routes. Fire extinguisher and hydrants has been prepared at each classes, each laboratories, and another places in accessible locations. In addition, a fire engine is stationed on campus in case of an emergency. A first aid kit is kept in each classroom and laboratories, just in case of injury. If students in critical condition, there is a clinic on the IPB campus that open 24 hours a day. This clinic provides inpatient care and an ambulance for bring the patient to the nearest hospital. To prevent the spread of COVID-19, health protocols such as social distance and hand sanitizers are placed at every classroom, laboratory store, and at the wall where there are many potential people doing activities. Furthermore, sinks are placed at campus or field for washing hands.
Academic program desk in Agronomy and Horticulture Study Program all has been certified for A level from National Board of Accreditation for Higher Education and ASEAN University Network Quality Assurance 2013 to 2017. The academic administration and learning process have been certified by Sukufindo International, SNI ISO 9001. Academic atmosphere at Agronomy and Horticulture Study Program is very conducive. For education and research, we collaborate theory and practice in the curriculum. Domestic students have the opportunities to participate in student mobility or student exchange program to other universities, such as ASEAN International Mobility for Students, Swiji Service Learning Program, Summer or Winter Course, International Internship to Netherlands. Agronomy and Horticulture Study Program fully support non-academic activities for students to enhance soft skills, leadership, and entrepreneurship, such as student association, sport and art, international and national competition, festival, and others. research activities at Agronomy and Horticulture Study Program is very intensive. We have produced new crop varieties and production technologies in addition to scientific papers and awards. Agronomy and Horticulture Study Program has reached its collaboration with many national and international research institutions.
Program Studi Pasca Sarjana Agronomi dan Hortikultura menyelenggarakan pendidikan Magister Agronomi dan Hortikultura dan program doktoral dengan 2 peminatan, yaitu Agronomi dan Hortikultura dan Ilmu Benih. Agronomi dan Hortikultura adalah ilmu yang mempelajari pengelolaan sumber daya nabati untuk menghasilkan produksi maksimum dan berkelanjutan melalui rekayasa lingkungan dan fisiologi tanaman dengan memanfaatkan potensi genetik pada tanaman agronomi, hortikultura, dan sumber bioenergi. Kami menghasilkan Magister Agronomi dan Hortikultura yang mampu mengembangkan ipteks yang unggul melalui penelitian mutakhir dengan kaidah yang benar untuk menemukan solusi permasalahan di bidang agronomi dan hortikultura. Kami menghasilkan doktor yang mampu mengembangkan dan menghasilkan kebaruan dalam ilmu pengetahuan dan teknologi di bidang agronomi dan hortikultura secara mandiri untuk menemukan solusi permasalahan melalui pendekatan interdisiplin, multidisiplin, atau transdisiplin. Mahasiswa pasca sarjana agronomi dan hortikultura mempunyai kesempatan untuk mengikuti double degree, summer course, winter course, credit earning dengan mitra perguruan tinggi di luar negeri. Program studi Magister AGH terlibat di dalam proyek SWAM yang merupakan konsorsium dari 3 perguruan tinggi dari Yunani, Portugal, Italia, dan 1 lembaga training di Eropa, serta 8 perguruan tinggi dari 4 negara di Asia, yaitu Vietnam, Laos, Cina, dan Indonesia. Tujuan dari proyek ini adalah membekali pemangku kepentingan pertanian dengan pengetahuan, keterampilan, dan kompetensi di bidang teknologi, agrolingkungan untuk pertanian berkelanjutan.
By using precision farming and smart irrigation, whether in greenhouse or open field, the plant will be able to get the exact fertilizer and water irrigation. And in addition, applying of silica will be able to improve plant resistance toward disease and pest, and also can improve quality of melon.
Saya meneliti mengenai tindakan agronomi dan lingkungan terhadap kejadian self pruning pada tanaman jeruk nipis. Self pruning ini bermanfaat untuk mengurangi atau mengefisiensikan biaya pemangkasan.
Saya mengkaji pemberian cahaya buatan secara agronomis, fisiologis, dan mikro-RNA terhadap tanaman buah mangga untuk mempercepat masa juvenil.
Topik riset saya untuk studi doktor ini terkait dengan karakter morfofisiologi beberapa genotipe padi yang kita tanam di secara tanam benih langsung atau dikenal dengan direct seeding of rice. Tujuan besarnya sebetulnya ini adalah untuk mendukung bagi para pemulia tanaman untuk bisa mengembangkan varietas ataupun galur-galur harapan yang bisa ditanam secara benihnya secara langsung pada lahan sawah maupun lahan kering.
Radiasi matahari yang tinggi pada musim kemarau menghasilkan beban cahaya dan panas yang berlebihan pada daun dan buah. yang memiliki dampak negatif terhadap pertumbuhan dan hasil tanaman. Oleh karena itu, saya menguji 20 jenis cabai rawit pada intensitas cahaya rendah yang akan memperoleh informasi terkait aspek morfologi, fisiologi, dan hasil yang berhubungan dengan toleransi pada intensitas cahaya rendah.
Indonesia memiliki 20,1 juta hektar lahan pasang surut dengan kandungan pirit yang tinggi sehingga tidak dapat dimanfaatkan untuk budidaya tanaman secara maksimal. Teknologi budidaya jenuh air yang dikembangkan oleh jurusan Agronomi dan Hortikultura IPB University berhasil menekan oksidasi pirit di lahan pasang surut sehingga meningkatkan pH tanah. Dari berbagai kajian yang telah dilakukan, teknologi budidaya jenuh air mampu meningkatkan produktivitas lahan pasang surut hingga mencapai 2-3 kali lipat.
Selama berkuliah di Magister Agronomi dan Hortikultura, saya berkesempatan untuk mengikuti program pertukaran pelajar di Warsaw University of Life Science, Polandia. Masih banyak kesempatan lain yang bisa kalian dapatkan di sini.
Saya masuk ke program studi Magister dan Doktor PSAGH melalui program beasiswa PMDSU. Dan selama saya mengemban perkuliahan di PSAGH, saya memiliki kesempatan untuk melakukan sebagian dari penelitian saya di Jepang. Hal ini karena dosen-dosen di PSAGH memiliki kemampuan networking research yang luar biasa, sehingga mahasiswa memiliki kesempatan yang lebih baik untuk dapat mengembangkan penelitiannya.
Nama saya Diar, saya merupakan alumni S2 dan S3 AGH IPB tahun 2015, lulus tahun 2019. Kesan saya selama studi di IPB adalah lingkungan akademik yang kondusif sehingga mahasiswanya menjadi lebih produktif. Kami dibimbing oleh dosen-dosen yang sangat berkompeten dan kami juga banyak diekspos oleh kegiatan yang bersifat internasional. Kebetulan saya pernah mendapatkan kesempatan untuk summer course di Kasetsa University Thailand selama 1 bulan.
Saya merupakan alumni program studi Agronomi dan Hortikultura Institut Pertanian Bogor tahun 2020. Permasalahan di bidang pertanian merupakan hal yang mendorong diri saya untuk belajar di program studi Agronomi dan Hortikultura IPB. Saya mendapatkan banyak pengetahuan baik secara teori maupun praktek di lapangan. Kemudian dukungan dan fasilitas pembelajaran dari dosen program studi AGH IPB membuat saya mampu berkembang dan berinovasi. Selama di IPB, saya berkesempatan untuk mengikuti kegiatan International Conference dan Winter Course di Ibaraki University, Jepang. Selain itu, saya juga mendapatkan kesempatan untuk mendapatkan beasiswa Tanoto Foundation saat kuliah di IPB.
Saya Seri, alumni dari program studi Agronomi dan Hortikultura IPB tahun 2020. Saya masuk ke program studi ini pada tahun 2018. Selama menempuh pendidikan di program studi Agronomi dan Hortikultura, saya masih bisa mengembangkan minat saya di bidang wirausaha. Pada tahun 2019, saya berkesempatan untuk mengikuti ajang pemilihan wirausaha muda berprestasi dari Provinsi Jawa Barat, juga dari Kementerian Pemuda dan Olahraga Republik Indonesia. Pada tahun yang sama, saya mendapatkan penghargaan sebagai juara 1 di bidang industri pertanian dan kelautan, baik tingkat provinsi maupun tingkat nasional. Selain itu, di tahun yang sama, yaitu tepat di Hari Sumpah Pemuda, saya juga mendapatkan penghargaan sebagai wirausaha muda berprestasi di bidang pertanian dari Kabupaten dan Kota Bandung. Selama mengikuti perkuliahan di program studi ini, saya juga masih bisa mengembangkan seluruh potensi dan minat saya di bidang wirausaha, sehingga di tahun yang sama ketika saya mengikuti program studi ini, saya mendapatkan penghargaan dari Yayasan Trubus Bina Swadaya, yaitu penghargaan Trubus Kusala Swadaya sebagai Duta Inovasi dan Penggerak serta Pemberdayaan Petani Indonesia. Saya bersyukur bisa mengikuti pembelajaran di program studi ini karena didukung oleh para dosen yang sangat suportif, juga didukung oleh staf yang sangat suportif.
Mari bergabung bersama kami di program studi AGH.
Selama di program studi PBP, saya banyak belajar tidak hanya terkait pemulihan konvensional, tetapi juga jalur bioteknologi dan juga mutasi, dan juga manipulasi genetiknya.
Saat ini saya sedang meneliti tentang kelapa, khususnya di bidang molekuler. Saat ini saya menggunakan marka SSR dan SNFP melalui gen pertambahan tinggi tanaman. Motivasi saya memasuki program studi ini adalah untuk mengeksplor lebih dalam lagi keragaman tanaman kelapa. Oleh karena itu saya melakukan penelitian di bidang molekuler ini.
Motivasi saya memasuki program studi pemulihan dan bioteknologi tanaman, di mana saya ingin mengeksplor diri dan mendapatkan pengalaman dari dosen-dosen pengajar yang profesional di bidangnya.
Motivasi saya memasuki program studi pemulihan dan bioteknologi tanaman adalah karena fasilitas yang ada di PBI sangat lengkap.
Motivasi saya mengambil program ini adalah saya ingin menciptakan varietas tanaman yang bermanfaat bagi umat manusia.
Saat ini saya sudah memasuki semester 2 dan sedang melakukan penggaluran tanaman jagung. Alasan saya masuk jurusan program studi ini adalah saya ingin menjadi breeder yang handal. Dan dosen-dosen di program studi pemulihan dan bioteknologi sangat unggul dan kompeten.
Yang menarik dari program studi ini adalah saya dan teman-teman bisa belajar tentang pemulihan secara konvensional dan juga bioteknologi dari dosen-dosen yang handal, serta telah menghasilkan inovasi-inovasi yang baru dan mutakhir dalam bidangnya.
Riset-riset yang dilakukan di program studi pemulihan dan bioteknologi tanaman ini difasilitasi dengan fasilitas yang cukup memadai serta lengkap. Oleh karena itu, penelitian di bidang ini dapat berjalan dengan lancar serta menghasilkan inovasi-inovasi yang mutakhir.
Penyelenggaraan proses studi pada program studi pemulihan dan bioteknologi tanaman didukung oleh para dosen yang sangat berkualitas, prasarana pembelajaran yang sangat baik, kebun percobaan dan laboratorium yang terkelola dengan sangat baik, serta atmosfer akademik yang sangat kondusif.
Di program studi pemulihan dan bioteknologi tanaman ini, kami menempa anak bangsa untuk menjadi pemulia tanaman yang handal melalui pendekatan pemulihan konvensional maupun bioteknologi di tingkat seluler maupun molekuler. SDM yang handal di bidang pemulihan dan bioteknologi tanaman, karena itu melalui studi pemulihan bioteknologi tanaman sekolah pasca sarjana IPB, kami siap untuk mendidik anak bangsa.
Program studi pemulihan dan bioteknologi tanaman mendidik calon-calon pemulia tangguh yang mempunyai latar belakang ilmu yang kuat gabung bersama kami di program studi ini.
Di program studi pemulihan dan bioteknologi tanaman sekolah pasca sarjana Institut Pertanian Bogor.
Ayo, mari bergabung di program studi pemulihan dan bioteknologi tanaman.
Ayo bergabung bersama kami di program studi pemulihan dan bioteknologi tanaman.
Mari bergabung di program studi pemulihan dan bioteknologi tanaman.
Ayo bergabung bersama kami di program studi pemulihan dan bioteknologi tanaman.
Mari bergabung di program studi pemulihan dan bioteknologi tanaman.
Mari bergabung di program studi pemulihan dan bioteknologi tanaman.
Mari teman-teman, bersama kita bergabung pada program studi pemulihan dan bioteknologi tanaman Sekolah Pasca Sarjana IPB.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak Ibu semua. Selamat datang di acara webinar AGH BIMTEK AGH ke-7 tentang teknik alat likor, pengambilan data dan analisis data fotosintesis, water efficiency dan transpirasi. Di sini saya sebagai MC dan juga moderator akan memandu acara pada di sini sudah banyak yang hadir Bapak Ibu, baik di ruangan sidang 1 dan 2 Departemen Agronomi dan Hortikultura dan juga Bapak Ibu di Zoom. Mudah-mudahan semuanya selalu sehat. Baik Bapak Ibu, pertama kita akan menyanyikan lagu Indonesia Raya dan himne IPB untuk sebagai pembukaan. Silakan Pak Mas Saiful. Baik, kita lanjutkan acara webinar kali ini. Pertama mungkin selamat datang kepada Ketua PPSN, Bapak Marsikal Madya TNI Purnawirawan Daratmo SIP yang selalu membersamai kegiatan webinar AGH. Selamat datang Bapak Daratmo.
Terima kasih.
Dan Bapak Ibu semua yang telah hadir di ruang Zoom maupun ruang sidang Departemen Agronomi dan Hortikultura. Perkenankan kami mengundang Ibu Dr. Eni Widajati sekaligus untuk membuka acara webinar hari ini. Silakan Ibu Eni.
Terima kasih Pak Deden. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semua. Puji syukur hari ini kita di Departemen Agronomi dan Hortikultura bisa melaksanakan webinar dalam bentuk BIMTEK yang ke-7. Pada kesempatan ini kami menyampaikan permohonan maaf bahwa Dekan Fakultas Pertanian Prof. Suryo Wiono dan Ketua Departemen Agronomi dan Hortikultura Prof. Edi Santoso sedang ada kegiatan yang lain sehingga mungkin nanti akan menyusul di webinar kali ini. Pada kesempatan ini juga kami menyampaikan ucapan terima kasih dari University Putra Malaysia, Bapak Dr. Muhammad Nasim bin Zafar, kemudian ada Bapak Toh Liang Su, dan Bapak Muhammad Afiq bin Kamar Sali. Juga kepada PT Unitama Analitika Perkasa, kami ucapkan kepada Bapak Gitsu Ginting, Bapak Rahmat Reza, kemudian ini Ibu ya, Bapak juga, Bapak Ilhami Mufti Arif ya. Terima kasih pada kesempatan ini akan sharing terkait dengan penggunaan alat likor dengan topik webinar hari ini adalah teknik alat likor, pengambilan data dan analisis data fotosintesis, water use efisiensi dan transpirasi. Terima kasih juga kepada hadirin yang ada di Zoom. Mudah-mudahan BIMTEK kesempatan ini terkait dengan penggunaan alat likor yang kita tahu semua bahwa di dalam penelitian bidang pertanian, saya kira alat tersebut memang sangat penting untuk mendukung data terkait proses-proses fisiologi, proses metabolisme di dalam tanaman yang kita bisa menganalisis lebih mendalam terkait dengan produksi maupun juga saya kira bermanfaat juga bagi rekan-rekan yang bekerja di bidang breeding atau pemuliaan tanaman. Oleh karena itu, kesempatan yang sangat baik ini barangkali kita bisa manfaatkan secara detail. Nanti Bapak Dr. Muhammad Nasmin akan menyampaikan terkait ada lecture-nya, kemudian juga nanti kami di offline ini kita juga sudah menyiapkan alat likornya, jadi nanti akan disampaikan juga bagaimana penggunaan secara praktis alat tersebut. Mudah-mudahan walaupun diikutinya secara daring, itu juga akan bisa dipahami secara baik. Sebetulnya kita mengharapkan juga di ruang sidang ini ada mahasiswa yang akan atau dosen maupun mahasiswa yang akan menggunakan likor ini bisa hadir secara luring begitu, sehingga akan lebih memahami dan diskusinya juga akan lebih mendalam saya kira. Namun demikian tidak mengurangi kesempatan ini, Bapak Ibu bisa juga menggunakan media dengan Zoom meeting yang telah kami siapkan. Mudah-mudahan Bapak Ibu bisa menerima kuliah maupun praktik yang akan kita laksanakan hari ini. Saya kira tidak akan panjang lebar supaya kuliah maupun praktek terkait dengan alat likur ini bisa dijelaskan secara mendalam. Apabila nanti ada hal-hal yang mungkin perlu ditanyakan, saya kira di sini Dr. Muhammad Nasmin dan tim teknis dari PT Unitama Analitika Perkasa siap untuk membantu Bapak Ibu untuk konsultasi hari ini maupun untuk selanjutnya. Barangkali nanti Bapak Ibu ada di institusinya, ada yang tertarik untuk menggunakan likor, saya kira bisa menanyakan lebih detail bagaimana teknis penggunaan alat likor tersebut maupun bagaimana memelihara alatnya supaya bisa digunakan dengan baik. Kalau menurut Pak Nasmin tadi alatnya harus sehat katanya ya. Jadi alat itu juga perlu check up dan sebagainya. Jadi silakan Bapak Ibu yang saat ini memiliki likor atau mungkin nanti akan membeli alat likornya, saya kira bisa berkonsultasi lebih lanjut. Baik, saya kira tidak panjang lebar, webinar kali ini akan kita buka. Bismillahirrahmanirrahim. Terima kasih Pak Deden, semoga webinarnya bermanfaat.
Baik, terima kasih Bu Dr. Eni selaku Sekretaris Departemen Agronomi dan Hortikultura. Baik, kita akan lanjutkan ke acara inti dari webinar ini, yaitu kuliah dan juga mungkin nanti ada demonstrasi ya dari Bapak Dr. Muhammad Nazmin Yapar. Beliau merupakan senior lecturer dari Department of Crop Science, University Putra Malaysia. Beliau menamatkan S1 di UPM, di Agricultural Science, dan PhD di Rice Physiology di University of Sheffield, UK. Berbagai penelitian dan juga research grant diraih oleh beliau yang semuanya di bidang fisiologi. Mungkin Bapak Ibu bisa Google Scholar beliau untuk tentang terkait dengan aspek penelitian yang beliau sudah lakukan hingga saat ini. Mungkin nanti Pak Dr. Nazmin akan menyampaikan bisa dalam bahasa Inggris ataupun dalam bahasa Melayu. Mungkin dan juga Bapak Ibu semua juga bisa berinteraksi melalui Zoom ini jika ada hal-hal yang ingin ditanyakan ke beliau mengenai tentang misalkan tadi tentang faktor fisiologi dengan penggunaan likor ini yang mungkin di tempat institusi Bapak Ibu sudah ada, tetapi mungkin masih kurang jelas pemanfaatannya lebih optimal seperti itu. Mungkin langsung saja ya kepada Bapak Ibu semuanya, kita dengarkan kuliah atau lecture dari Bapak Dr. Muhammad Nazmin Yapar. Silakan.
Oke, terima kasih atas pengenalan. Jadi saya tak buang masa, oke? Saya akan terus sampaikan. Jadi acara ini ada dua bahagian. Kita ada bahagian kuliah, lecture, dan juga bahagian demonstrasi. Tapi mungkin dalam masa yang sama mungkin ada sedikit hybrid overlap sebab kita nak tunjukkan alatan itu. Jadi saya sampaikan kuliahnya dalam bahasa Inggeris. see. Apa? Oh, connection ni hilang. Jadi ini boleh dengar? Okey. Saya cuba ni sekejap Ditembak mana ni? Kiri, kanan? Dia macam tak ke depan. Tidak stable. Tapi dia bergerak tak? Okey. Delay. Okay. Today we're going to three equipments today. So pardon for the delayed response on the slides on the screen at the moment. So we are very lucky and fortunate today because Pertanika Unitama Perkasa, long name for a company. They are very to share with technology for today. So I'm going to start with mungkin Bapak boleh tolong ke depan kan? Okay. So I'm going to give some, maybe I don't want to call it introduction, maybe we call it revision about photosynthesis, because I'm very sure that many people at some point in their life, they have actually learned photosynthesis, but the depth of photosynthesis, the detail of it might be overwhelming sometimes, unclear, or it gets tangled up in various ways, right? So we're going to have a look at the revision of photosynthesis. Then I'm going to introduce three equipment that can be used extensively to study photosynthesis. So we have the LICO 180, which is the spectrometer. That's the little black guy on the far left. And right in the middle, we have the LI60. Oh, sorry. In the middle here is LI600, which is the porometer, fluorometer, and finally we have the most expensive of them all, which is the LI6800, the portable photosynthesis. I think many of plant physiologists are more familiar with the older version, the older generation of 6400. Okay, boleh maju Bapak? Right. So undoubtedly, photosynthesis is the most fundamental process on this planet, on planet Earth, without which life is out of questions, because it is the very process that joins in raw materials that can be found on this planet and turn it into something useful, something of essence to be used by all organisms on the planet. Okay, so what I have on the slide here, this is the cross section of a leaf, a typical leaf, and it looks very busy. So in the leaf, there are various types of cells. So those cells that actually do photosynthesis, we call them as mesophyll cells. And the mesophyll cells itself have two types, the palisade and spongy mesophyll. So I would like to take you into a journey way into the cell itself. When you go into the cell, let's zoom in and look, what is the kingdom inside the cell? Because this is where the photosynthesis takes place. Okay, so in the plant cells, this green thing it looks like some kind of ball, right? That's a chloroplast. So chloroplast is one of the many organelles that are present in the plant cells. We have a nucleus, we have mitochondria, and some other organelles. But today we're going to focus just on the chloroplast. So for the chloroplast, when we take a cross section of it, there is a further divisions inside the chloroplast itself, the anatomy of the chloroplast. And this is very important because the process of photosynthesis happens in various locations inside the chloroplast itself. We know that the chloroplast itself is super small, ultra structure, but inside of it, there is something even smaller. And this is where the photosynthesis takes place. Maju Bapak. Right. Okay, so on the slide here, it shows you on the far left, that is the journey of CO2. Okay, so we all know that photosynthesis requires ingredients, and the primary ingredients are CO2, water, some nutrients, and also light. Okay, so the CO2 will have to travel from the outside of the leaf. That is the picture over here. And then it has to somehow go through various membranes and also walls before it can reach chloroplast. So the reason I'm showing you this diagram here, to show you it is not a linear or simple way for the CO2 that we have in abundance surrounding us to reach chloroplast. If the CO2, carbon dioxide, does not able to reach chloroplast, no photosynthesis would have occurred. But the journey itself is very difficult. You can see there are many cells that it has to go through. There are many membranes that it has to go through. Then it also needs to change phase from the gaseous phase into the liquid phase, and then gets into the chloroplast here. Right. So once the CO2 is in the chloroplast, with some light, water, and nutrient, photosynthesis can start to happen. But let's see the locations inside the chloroplast itself. So in the chloroplast, it is divided into the photosystem structure and also the biochemical part of it. So the thing that you look like a stacking of structure here, this is called the granum. And this thing, each single disc is where the light reaction of photosynthesis takes place. This is, you can regard it as the antenna for light. This is the solar capture for the chloroplast, right? And just outside the granum here, you will have the surrounding environment, the soup, I would like to call it a soup, inside the chloroplast. And this is the second part of the photosynthesis happen, which is the production of sugar. So it's very important. Photosynthesis is never linear, and the process, the reaction that takes place happens in a specific compartment. So, yeah. So this is the basic of photosynthesis. Do understand that the reactions in photosynthesis is divided into two. Hence the name photosynthesis. The photo means the light reaction, which happens on the grana here. And with the light dependent reactions, we get products. And this is the important products, namely the ATP and also the NDPH. So what are these two molecules? So ATP is the energy currency for all cells, not only in plants, but in humans as well. And also the NADPH. These is electron donor. So whenever this molecule is passing around, it is able to donate some of its electron, okay, to those who are in need. And these reaction also have byproduct. And oxygen is the byproduct, and this is the thing that we breathe in for our own livelihood, right? So that's the first part of the photosynthesis. For the second part is the Kelvin cycle. This part does not require light specifically, directly, but it requires the light reactions to get ATP and NADPH so that the cycle, the Kelvin cycle for these reactions can happen. And this is the reaction where we get the sugar, right? So just a quick recap, the first part of photosynthesis, to gather energy in two forms, namely ATP and NADPH. For the second part of photosynthesis, the energy from the first part will be used to synthesize the sugar, right? The glucose that we usually know, right? Boleh maju? Maju apa? Oh, okay. Oh, sorry. Okay. So this is the summary of it. Whatever that I just said just now. Have light reactions. We got NADPH and ATP, and then Kelvin cycle will use it up. So you can understand now why it is important to understand the photosynthesis based on the reactions. Because, for example, at least for the products that we have from LICO here today, both reactions can be measured separately or simultaneously, right? Is it possible untuk kamera tunjuk ke machine? Yeah, all right. So for the purpose of our demonstration today, we are to focus on the light, how to measure light that is perceived by the chloroplast so that it can generate all this energy for the production of Kelvin cycle, right? So we have the first equipment here, which is, where's the porometer? This equipment here. Yep. So this equipment here, it's called porometer fluorometer. This equipment will specifically, boleh maju apa? Maju ke depan, satu. Okay, yeah. Oh, sorry, not this one. That's. Yeah. We all know that light is one of the ingredients in photosynthesis, right? So in order to energize the whole photosystem, the correct amount of light, the correct quality of light needs to be present for the photosystem. Otherwise, the end product, the ATP and NADPH, is not going to materialize. So this equipment that I'm holding on my hand here, this is spectrometer to measure, is the light enough and is the light correct? So I think many of us agronomists in agriculture, we need to understand one thing about light. Light has a dual properties. So you need to measure light in the sense of, is the quality correct? And also, is the quantity correct? So when I talk about light quality, that is referring to the color. Like in here, the color. So we know that sunlight has so many color, but not color is going to be used for photosynthesis. And then also the light quantity, the number of light particles that the photosystem perceive. So when these two things are correct, then the first part of photosynthesis will happen in the right manner, right? So for the second here, this is actually to measure the fluorometer here, how much light is captured by the photosystem, if you're referring to the slide. Light capture is one thing, but does it use the light or not? So this machine will also tell you that as well. How much light is captured by the leaf, and then after it has captured, does it use to produce ATP or NADPH? So there's two things there, maximum quantum yield and also the efficient quantum yield, right? Okay, boleh maju Pak? Yeah. Yeah. So this is the quick recap of what I just said just now. So light quantity, light quality, and also the period of the light. So this is very important. Much of the agronomists or agriculturists that I have dealt with, horticulturists, they kind of missed these points, right? So these need to be given a proper amount of attention because it's an ingredient of photosynthesis, right? So you have to get it right, right? So you might wonder, if you look at the light quantity on the slide, at the bottom, it says micromole. Yes, this machine here, all the machine today that we have from LICO here, can measure the number of light particles. It's very small, you cannot see it, but the sensor of the machine can actually tell how many are actually in presence, right? Okay, so boleh maju. Yep. So this is about this machine here, this piece of equipment. So we talk about how much light has been captured, but what about the captured light? What does it do in the cell? Does it do something or otherwise? So this is the study of fluorescence. Okay, the fluorescence actually, simply put, is the measure of glow in the dark of the leaf. In the ideal world, whatever the leaf has managed to absorb, it uses it all. But leaf is not a perfect system. Some amount of light is actually released back to the atmosphere because the plant just cannot deal everything at once. Yeah. For example, you might have 10 plates of fried rice in front of you, but you are only able to eat maybe 5. So what happened to the 5? So these 5 needs to be returned to some place, right? So your capacity is only to eat 5 plates of rice. So that is the maximum quantum efficiency, which regularly in fluorescence is known as FV over FM. Yeah. The second measure, which is on the right on the slide, which is phi PS2. Phi is the Greek letter, okay? Phi PS2. Out of these 5 plates of rice that you have ingested or consumed, how much actually turn into your energy that your body can use? So that is the equivalent analogy for this situation here. So the light that has been absorbed by the leaf, does it do the job to produce energy or not? So this machine here measure it in the form of phi PS2, the efficiency of the quantum absorbed. Right. Okay. Right. Okay. What about the second part of photosynthesis? So that would be the Kelvin cycle. Now remember your at the beginning, I told you about the location of the chloroplast. For the light reaction, it happens on the photosystem, the thylakoid membrane. Now we move to the second location in the chloroplast, which is the stroma, the soup surrounding in the chloroplast. So in the soup, another biochemical reaction happens, and this is popularly known as the Kelvin cycle, right? Look at the name, the Kelvin cycle, means that it is a cycle. It is not a linear process. Because it is a cycle, it needs energy. This is why light reaction is very important. The energy acquired from the first part of the photosynthesis will be used to energize the second reactions for the Calvin cycle. There's a question here. Bagaimana perbezaan fotosintesa dan tanaman sitiosa? I will answer that after we finish that, because that is more about the structure of the leaf. Okay, can you jot down so that I don't forget the question just now? Thank you. Just ask the question on the chat. Apparently ada chat ya. Boleh di boleh kumpul nanti. Saya jawab di hujung. Boleh ya? Okay. So Kelvin cycle. It is a cycle. It requires energy. We do the cycling using bicycle. We also need energy. So the energy is provided by the first part of photosynthesis. So the Kelvin cycle itself, it comprises 3 phases, namely the stage 1, the carbon fixation, and then moves to the reduction, and then regeneration. Yeah. For the equipment from Lycor, it specifically measures the first part of Kelvin cycle, which is the carbon fixation. And that job is done by this machine here. Can you turn this so that the camera can see? So this machine is called LI 6800. Actually, you can just flip the screen. Right, my student is very nervous. Yeah, super nervous. Yeah, one moment they are in Malaysia, in KL, now they are in Bogor. Right, so this machine here, it measures the first part of the Kelvin cycle, which is the carbon fixation. On the screen, it is denoted as A. A stands for assimilation. And look at the unit, micromole per square meter per second. Micromole of what? Micromole of CO2. How much CO2 is fixed into the system per given area per second, right? So now you can understand, if you have a happy and healthy photosystem, it will only make this cycle to go faster and faster. And what is the consequence? The moment you have that, you will start to have your sugar precursor. You see, glucose is not manufactured directly out of Kelvin cycle. The first sugar precursor actually happens in the second part of Kelvin cycle, which is the reduction of 3-PGA. PGA stands for phosphoglycerate. Okay, maybe I can briefly tell you what's going on here with the Kelvin cycle here. Okay, so we have our ingredient of photosynthesis, the other ingredient of photosynthesis, which is carbon dioxide. Carbon dioxide will combine with the 5-carbon sugar, ribulose bisphosphate, 5-carbon sugar, which is already present in the chloroplast. Okay, don't ask it came from where, it's already there. So this 5-carbon sugar combines with CO2 with the help of special enzyme called Rubisco. So Rubisco kind of like the matchmaker. You got one couple here, one couple there, join together. So it joins together, but this molecule is unstable. Immediately it will split into 2, producing this PGA, phosphoglycerate, 3-phosphoglycerate. It only has 1 phosphate attached to it, okay? And then this will be converted with the help of ATP. You see it here. Where does it come from? From the light cycle earlier, the light reaction earlier, right? So, and then with the addition of hydrogen to this phosphoglycerate, it now will become reduced, meaning that it has extra hydrogen to it. And eventually it will become this sugar precursor that we all know about, GA3P, glyceroldehyde 3-phosphate, or some books call it triose phosphate. Okay, different names, just synonym. It's the same thing. 3-carbon sugar. So 2 times of this 3-carbon sugar, you will get your glucose, right? What about this regeneration of RUBP? You see, mathematically, this Kelvin cycle is very smart. It knows if it simply fix one molecule of RUBP and one molecule of CO2, it will stop here. It cannot go further. So the cycle actually happens simultaneously to fix 3 molecules of RUBP and 3 molecules of carbon dioxide. Right? Maybe I can do some mathematics to show you how does it work. So in the carbon fixation, oops, hasn't got I don't think you can see it. Do you have marker? 1 minute, we're going to find a marker. Or maybe can faktor iklim apa? Oh, okay. All right. It's carbon fixation. Yeah. So for the Kelvin cycle, this Kelvin cycle, if this cycle is only fixing 1 time of RUBP plus 1 times of CO2, this is going to be linear. No extra. So in reality, what happens is 3 times of RUBP go together with 3 times of CO2. So to produce 6 molecules of 3-phosphoglycerate. In terms of carbon, RUBP is 5 carbon. So in here, 3 times 5, you got 15 carbon. 3 times 1 carbon of CO2, you got 3 carbon. Okay, so in total here, you got 18 carbons. At the end of reduction phase, like I said earlier, 1 molecule of G3P will exit. See here, 1 molecule of Ga3P will exit. Meaning that at the end of reduction, 18 carbon minus 3 carbon. 3 carbon is the G3P because this one exit. So what is left is 15 carbon of molecules. From where? From 5 molecule of this thing, G3P. Remember, okay, this thing does not exit, only this thing exit. This thing continue with the cycle. So from this 15 carbon, the cycle rearranges the molecules from this 15 carbon of 5 molecules of G3P, they change it into 3 molecules of RUBP. And we know that RUBP is 5 carbon, 5 times 3, you got back your 15 carbon. So that's in short, that's how it works. Okay, just a small warning. I have simplified it super simple. In reality, if you learn physiology in depth, there are 10 steps here. From here to here, there are 10 steps involving enzymes name even I cannot pronounce. So difficult. Right. Okay. Right. Boleh maju, Pak. So that's the Kelvin cycle, which is measured by this equipment here. Apa lagi? Ke depan. All right. Okay. Sabar ya dengan soalannya. All right. So with that in mind, the capability of the Lycor 6800 it is not only to measure the photosynthesis on the spot. You can actually measure photosynthesis at various light concentration. With this information, you just produce what we call as response curve. Why is response curve important? So that you know the identity of the leaf that you are working with. Because in nature, leaves are categorized based on the light requirement into sun leaf and also shade leaf. And these two leaves are different biochemically and also structurally. Right. So let's say that with this equipment here, see, this is the equipment that you saw earlier. Clamp your leaf, do the photosynthesis, and play around with the amount of light that this plant receives. The moment you create this, you can understand that, oh, this curve actually has two phases, the first phase and the second phase. And then the first phase, you know that up to this light point, around 300 micromole, at least for this plant, the light is limiting, right? So how does this relate to agriculture? Now you know that after you have produced a number of these, you can see that some plants actually have a shorter light limited region. This is around 300. Maybe you have plants that stops the first phase of light response curve at 250. So plants that have high light use efficiency, usually they have a good nitrogen use efficiency as well, right? So maybe you want to increase your efficiency of your plant. You can use this to decide, should I add more nitrogen to the soil? Because we know nitrogen is used to make chlorophyll complex, rubisco enzyme. Chlorophyll complex is meant for the photosystem to capture the light. So when the plant is able to capture more light, more energy will be produced. If the plant uses nitrogen to make more rubisco, more CO2 is fixed. Therefore, you got more sugar, right? So the capability of this equipment is very, very extensive, okay? You can go very, very deep about it, right? Okay, Terapan. Yeah. So for the question, this is I got from Pak Edi. He asked me to talk a bit about transpiration and water use efficiency. Another ingredient of photosynthesis, which is water. What about water? Even though water is abundant around us, I would call it ubiquitous as well. It's present everywhere, but not all water are readily available for the plants, okay? So transpiration is the process of plants losing water through the actions of stomatal opening. You see on a piece of leaf, on the surface, you have all these pores of that can allow gas exchange. And since water can also present in the form of vapor, which is gas, so water can actually exit from the leaf. There are a few number of transpiration types. So today we are focusing on the stomatal transpiration, meaning that the exit of water through stomata. Yeah. If you are struggling to understand stomata, think of it like sweating. You know, human, we are sweating, right? You go play football or something, you are sweating. Why human are sweating? To cool down, right? So it's the same purpose for the plants. But for plants, there's another function of transpiration to pull nutrient from the root all the way up. Some trees are very tall. For example, like the tree, the sequoia trees in America, that is as tall as 120 meters. That tree hasn't got any pump, hasn't got any heart. So how come the water from the ground to reach all the way 120 meters up? Yeah, so one of the mechanism that the plants use to pull water all the way up is through transpiration, right? So transpiration, this is the regular transpiration that we see. this transpiration in the regular sense, it's simply about the evaporation. Okay, so I'm telling you this so that you are aware. There are better ways than transpiration to talk about water loss in plants. Okay, but if you take into account the action of stomata into the equation of transpiration, you see, transpiration got its own equation. But when you talk about the stomata, specifically transpiration due to stomata, the measure is actually more accurate, okay? Because stomata comes in various forms, various density. So using another parameter called stomatal conductance will give you a better understanding of how is your leaf water balance. Is it good or otherwise? Because in drought condition, you know, when there's not so much water around, it is important for the plants to close stomata. And we need to know whether the plants are closing stomata at the right time or not. So this is another side of the breeding actually that people are into. They call it micro breeding. They breed for the variety, for example, rice variety with correct stomatal size and arrangement. Because rice with the correct stomata, not only that they manage to preserve water in the plant successfully, but also to facilitate CO2 in and out of the tissue very, very efficiently. Right, Maju? Yeah, yeah. So from the stomata, because we want to understand about the water exiting the cells, so we can understand, is the plant efficient in terms of water use? So regularly, traditionally in physiology, people use this water use efficiency simply by having the assimilation value divided by transpiration. But again, I would like things to be more specific. Maybe you want to understand transpiration at your leaf level. So for that, there's another measure of water use efficiency, which is called intrinsic water use efficiency. In the formula, you divide assimilation with the stomatal conductance that you saw earlier. So when you understand this, we can understand for 1 molecule of CO2 fixed, how many molecules of water that is lost. Yeah, because stomata, when it opens, not only CO2 that gets in, water also can get out. Oxygen can also get out. Okay, so the plants needs to balance this. Should I open more? Should I open halfway? Or should I not open at all? Right, if the plants do not open stomata, can the photosynthesis happen? Pretty much not very happening, right? So the plants need to make a good decision and have a better control of stomata. So intrinsic water use efficiency is one parameter that you can use, which can be obtained by the 6800 LICOR as well. Right, Maju. Yeah. So why this is important? Yeah, understanding all this stomata, because it's very small. Nobody really pay attention to stomata. Stomata actually one of the components contributing to water cycle and also the carbon cycle for our atmosphere. Okay, so for example, I got a simple graph here. Got the time here in second and also the stomatal conductance. Yeah, so you can see that, for example, we got plants here, soy. What's soy in Indonesia? Kedelai. Kedelai. Kedelai is mule. No, don't go there. Kedelai. 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 Okay. Jauh bunyinya dari soya. Nampak apa? Macam mana S lompat ke K? So the kedelai bean experiment. So in the morning, you can see that the stomata is rather not opening very much because it is the light is still not as bright. Okay, so the photosynthesis, it's warming up. Yeah. But when you go mid-morning, waktu duha, it gets warmer, right? Look at the stomata here. It is a lot higher. Okay, so the opening of the stomata, which is reflected in the measure of stomatal conductance, is proportionately with the activity of photosynthesis. The more the stomata open, like this, the more CO2 that can get in. So the more CO2 can get in, the more sugar that can be produced by the Calvin cycle. And also not only that, actually, also to release oxygen. You see oxygen, when it's too much in the leaf, it's accumulating that kind of toxic to the leaf. So the plants need to release all the oxygen out so that you can use it, you can breathe, okay? So what happened for the tobacco in the midday? Same time, which is mid-morning, midday, more or less the same. But you can see that tobacco, since it is different species, the stomatal conductance are actually a lot higher. So by definitions, we can make a quick hypothesis that the growth between two plants, tobacco and soy, tobacco should be much faster in terms of growth. Even I don't have to go and look at the plants in the field. Just looking at the physiological data like this, we can already know this plant is actually growing a lot faster. Just look at the stomatal conductance. It's opening the stomatal pore like crazy, right? Yeah. So yeah, so this is stomata is one of the small things under physiology and agriculture, which is often overlooked. Okay, but if you pay good attention to it, for example, like doing the microbreeding that I mentioned earlier, something tremendous can be resulting out of it. All right. Okay, maju Pak. Maju ke hadapan. All right. Okay. All right. Itu sahaja untuk revision photosynthesisnya. Jadi saya tengok tadi ada soalan kan? Jadi kita boleh jawab soalan. Apa soalan?
Baik, terima kasih Dr. Mita yang sudah memaparkan kuliah kita pagi ini. Mungkin jika Bapak Ibu langsung bisa menanyakan langsung ya sambil nanti mengumpulkan yang di kolom chat. Silakan Bapak Ibu, jika ada yang ingin langsung ditanyakan bisa raise hand dan langsung menyampaikan kepada di forum ini. Silakan Bapak Ibu.
Mungkin boleh bacakan soalan yang dalam chat tadi. Apa ditanya?
Ya, yang pertama ada 3.
Apa?
Bagaimana perbedaan fotosintesis pada tanaman C3, C4, dan CAM yang tadi ditanyakan?
Okay. Ya. Oke. Jadi, jawab siapa? Inggris lagi kah? Sampai soalannya dalam bahasa Indonesia.
Bahasa Indonesia boleh. Mulai boleh.
Saya jawab bahasa Inggris ya. Campur-campur. Tadi apa? Katanya gado-gado. Campur-campur. Jangan gaduh. Gaduh-gaduh. Okay, perbezaan, the difference between 3 types of photosynthesis, namely C3, C4, and CAM. Most of the plants on planet Earth are C3 plants. Why? Because the first product of carbon fixation, C3, that you saw earlier, which is phosphoglycerate. For C4 plants, the first product of carbon fixation is for carbon, which is malate or oxalate. Okay. For CAM plant, kind of similar with C4 plants, but the timing is different. You see, the problem with C3 plants, during the afternoon time, the plants experiencing photorespiration. Okay, photorespiration is metabolically wasteful process. The plant is just trying to save itself. It is not doing anything. It's just consuming energy without no sugar product at the end. It's not like photosynthesis. You use energy, but you got sugar. Photorespiration, you don't have it. So C3 plant, it has this problem. So some plants, especially plants originating from Mexico, Brazil, the good example for this will be corn or maize, has evolved a new type of photosynthesis. It separates the carbon fixation into separate cells. So I don't have the picture here, but I can just imagine this way. For C4 plants, there are two compartments, two cells that do photosynthesis. For C3 plant, only one cell. Kevin cycle happening all in one cell. But for C4 plants, the first part of Kevin cycle, which is the carbon fixation, happens in the mesophyll cell first. And then it fixed in the form of 4-carbon compound called malate or oxaloacetate. It depends on the species, mostly malate. Okay, so these carbon compounds then move to the second cell, get transferred. Then in the second cell, this 4-carbon compound will undergo the release and the regular cycle of Kevin cycle. All right. So in this manner, we call it, it's separated by special compartment space. It is separated by space, spatial. For C4 for chem plant, this is for plants like pineapple, cactus. The first product also 4-carbon, but it's happening at night. Okay, the fixation, it's happening in the same cell, but at night. So pineapple, at night, it will completely open all stomata. It allows all CO2 to get in. The moment CO2 gets into the leaf, it will be fixed into the 4-carbon product, which is the malate. In the morning, pineapple will completely close the stomata, so no gas can come in. So in the morning, it will do the regular Kelvin cycle as usual. So for the chem plant, it is separated by temporal, by time. To achieve what? Special and temporal things. To achieve what we call as CCM, carbon concentrating mechanism. For what purpose? This thing, to fight photorespiration. Yeah. Ya, itu jawabnya. Right. Okay, ada lagi soalan?
Baik, kapan rubisco memacu fotosintesis dan kapan memacu fotorespirasi dan apakah ada faktor climate yang pengaruhnya rubisco?
Sekejap, saya nak kena proses dulu soalan tu. Mana je? Atas bawah. Hilang. Sekejap ya. Saya kena duduk Indon 1 tahun baru boleh melaju baca. Kapan rubisco memacu? What is memacu? Trigger. Yeah. Trigger. Kapan memacu fotosintesis dan kapan memacu fotorespirasi? Okay. Senang. Senang. Memang senang. Saya tahu kan. Bukan senang, gampang. Rubisco, dia ada, mari kita tengok nama rubisco. Rubisco itu dia dikenali sebagai ancient enzyme. Apa ancient dalam bahasa Indon? Lama, kuno, dahulu kala, purba. Ancient maksudnya kita selalu belajar di sekolah. In school, we learn that enzyme action is very specific. Key and lock, and then it opens one, right? One key to open one lock. But for the rubisco, 2 keys can open 1 lock. That is the problem. Okay, so the full name for this is ribulose bisphosphate carboxylase oxygenase. Okay, so nampak dia ada two biochemical reactions can be done. Carboxylase reaction and also the oxygenase reaction. So when does it happen? So a few things. So most of the time, it will do the carboxylase reaction. When it does carboxylase reaction, you got your sugar, regular one. When it does your oxygenase, no sugar. So when does it do the carboxylase or carboxylation reaction? When CO2 is high, oxygen is low, number one. And when temperature is around 25 degrees Celsius, it will do carboxylation reaction. The opposite of that, when CO2 suddenly drop, oxygen is a lot. For example, when stomata are closed, lots of oxygen built up. And also when it gets hotter and hotter during afternoon time. When that happens, the enzyme is deaf, pekak. Dia tak nampak, buta dah, dia tak nampak ni. It will use this oxygen reaction. So that's when. But when the situation becomes calmer, tenang kembali, Rubisco kembali ke oxygen carboxylation reaction, right? Okay. So,
ada pengaruh dari climate?
Yeah. Climate warmer, as it gets warmer, Rubisco less reactions per seconds of unit. And Rubisco, actually there is an enzyme, separate enzyme to activate it. It's called Rubisco activase. If suddenly there is a
Mohon maaf Bapak Ibu, internetnya sedang terputus. Mohon menunggu sebentar ya Bapak Ibu.
Sudah? Okey. Jadi saya sambung kembali. Jadi soalannya, apa hubung kait antara transpirasi dengan penyerapan nutrien? Okey. So nutrients, or actually ions of elements, they are actually dissolved in water, originating from the water soil water here. So soil water, so you have all these nutrients in. You have the ammonium, you have the phosphoric acid, and so on. So these are all dissolved in water, meaning that as water moves and travel, they will follow along. Okay, so it is very crucial for the water to be able to go upward. So transpiration facilitates this movement of water from the bottom of the plant all the way to the top of the plant by the action of water potential. Okay, so it's kind of a lot to talk about water potential. Let's put it this way: pure water, the water potential, which is the unit usually megapascal here. Pure water, H2O, 0 megapascal. The moment something is dissolved in the water becomes impure. There's contaminants in the water. It will become more negative. An example here. So at the root system, at the tip of the root, the water potential here, remember, okay, it's not just in the water, it becomes -2 because nutrient has been dissolved in this water. Okay, it will start to move towards a more negative water potential. Lots of water, it moves upward because in the upward region of the plants, the water potential is more negative. So the law is water potential will move to the more negative part of the water. Okay, as you go higher, the water potential is -5. And at the leaf level, the water potential is -10. What about water potential in the atmosphere? That is even more negative. That is -25. So the atmospheric water potential actually pulling the water all the way up. So as the water go up, the nutrients travel as well. Okay, so thank you to respiration. Okay, got it.
What is the optimal time to collect leaf sample and to measure stomata?
Oh. Collect maksudnya dikumpul.
Yeah. Maybe pengamatan, observation.
Oh, okay.
Time to
Okay.
see the
4 C3 plants. Sekejap, I need to convert into waktu Malaysia jadi waktu Indon. Berapa jam is it? Because I don't want to say 11. Sekejap ya. 11 Malaysia. Sini berapa? 10. Okay. Jadi sekitarnya untuk optimum fotosintesis dan juga stomatocanata untuk C3 plants jam 7.30 sampai sekitar 11.30 begitu. Ini waktunya. Tengah-tengah ini jangan buat apa-apa, berhenti, sambung kembali. 2:30 Malaysia. 1:30. I just put it 2 as well. So sekitar jam 2 sampai jam 1 hour before sunset, that should be 16. Just 16:30. Yep. Untuk C3. Saya jawab untuk C3 sebab kebanyakan pokok C3. Right? Nampak berhenti ni? Stop, jangan. Ini mid-day depression. Okay, itu waktunya. Ada lagi soalan? Apa itu?
How does the LICOR work mechanism and we can...
Okay. Okay, so I got a question from Nurfian. Okay, macam ni. Untuk soalan pertama itu, LICOR applications, it's not only for photosynthesis actually. You can use it to study respiration and also the water use efficiency that we saw earlier. So it's going to be very long to answer this one, but the advice is actually LICOR, the website LICOR itself, is very helpful. It's very helpful. So what I suggest you to do is to go to the LICOR, specifically the page of this product, and then find the tab there that says resources. Resources. Under the previous study, which has been done, how is it? Right. Okay. And the second one is, what is the relationship between the analysis of photosynthesis, transpiration, water? Okay. Sugarcane. I think sugarcane is C4 plant. Okay. Let's put it this way. With LICOR, even though most people use it to measure photosynthesis of C3 plant, it can also be used to study C4 plants. One thing about C4 plants is we know for sure the limit of carbon fixation has reached the roof due to this mechanism, carbon concentrating mechanism. Okay, so when you want to study fixation, pretty much usually very minimal difference you're going to find out. All right. However, there is light system that you can improve. Okay. So which is coincident with the demonstration today, use efficiency. So the terminologies that you're looking for is RUE. Radiation use efficiency. Okay, so for the question here, it asks the relationship of everything about the sugarcane. So sugarcane, we know the carbon mechanism is kind of at the roof because it is a C4 plant, but there is always a room for improvement. So for the room of improvement, go to study RUE because more energy is produced by the plants, the more the plants can actually produce other parts of the biomass. Other parts of biomass, not necessarily the harvested part. It can be other organs such as the vascular system and so on, which can help the plant to, example, flowering earlier or having a tougher plant. You know, sometimes some cornfield got hit by typhoon or something. So it's very important to have a stronger plant. So this is needed during the biomass partitioning. Okay, so with all this efficiency improve can help further biomass accumulation in the correct way. Okay. Okay, itu saja. Alright.
Baik, Bapak Ibu mungkin dari ada yang ingin langsung ditanyakan, silahkan langsung buka mic-nya dan bisa langsung ditanyakan. Silahkan Bapak Ibu yang ada di Zoom. Apakah ada Bapak Ibu? Atau ada demonstration? Mungkin kita langsung saja di demonstrasi penggunaan likor. Di sini memakai ada beberapa tanaman yang bisa digunakan, mungkin bisa melihat penggunaan likornya. Oke,
Alah. Tak deh, mau saya jawab di tepi-tepi. Siapa nak cakap ni? Okay. So we have Unitama. They are very shy, super shy. It's okay. So am I the one that's not shy enough? Right. So we have 3 equipment today, which is the first one. This is LI180. Can you turn this on, please? This is spectrometer. Spectrometer is to measure light spectrum. So from the light spectrum, 2 important information that you will get, namely the light quality and also the light quantity. Right. And the second piece of equipment is this two dual function, porometer / fluorometer. Porometer, you can use this to study water use efficiency because it gives you the reading of stomatal conductance. For the fluorometer, which is in this same machine as well, you can use it to measure photosynthetic efficiency, the 5 PS2, meaning that you know the leaf managed to capture what amount of light, and then the captured light, what does it do now? Does it do photosynthesis or does it do something else? Okay, so that is this equipment. The main star, the celebrity of this demonstration is actually this thing. You can buy a house with it. Or maybe 3 Avanza. More, actually, more. Okay, maybe 3 Innova Kijang. Very expensive, but because it means it's very powerful. Okay, I'll just tell you about this machine. How does it look like? Give the tour of the machine. Can you push? Careful. So this machine, LI6800, this is the new generation of the old LI6400. I think all of physiologists have worked with the old version of it. So this is a new version, all touch screen. Can you turn it this way? The screen, flip it. So this machine, it has a few parts. So the box here in the middle here, this is called the console. Okay, and we have all these wires here. These are the cables, the gas cables, transparent here, and also the signal cable. And finally, the measuring chamber. This is full spec. Therefore, it has got the fluorometer. So the fluorometer that is present in here is also present in here. Okay. So it's very, very capable. Right. So how does it work? So let's say that we have our plant here, right? And we want to understand how is for example, the Kevin cycle, the assimilation. So we clamp our plant and then we set the environment that the plant receives. It can be the similar situation as what the plant has been growing in, or some kind of hypothetical situation in the future. For example, we know in the future, the CO2 is increasing maybe to 400 ppm. We can change this to 500 ppm. Let's see. Change it to 500 ppm. Mau tolong tukarkan 400 ppm. Bukan ppm kan? ppm. Oh, okay. Tukarlah. Tukar jadi 500. 400 is the current. But in the future, very near future, it's going to be 100. Done. Yeah. So not only that you can change the CO2, you can do other environmental modification as well, involving the fan, the temperature, and also the light. So light I've been setting this at 500, but actually we want to increase it. So what is meant by light quantity? This thing here, micromole. So at the moment, the light is receiving the quantity of 500 micromole. Maybe you want to change it to 1000? Change it to 1000. Yeah, meaning that for 1 second, 1000 micromole of light is received by the plant. And that is light quantity. What about light quality? This machine can also change the light quality, which is this bit here. Maybe change the red to 85%. Oh no, 80%, and the blue to 20%. So light quality, we can see it in the form of color. Okay. Yeah, and then we can keep it. For it, you can keep it at 20%. That's fine. Yeah. So why only two lights or 3 lights? Because these are the 2 main color that is used to run the photo system in the chloroplast. Other colors are used as well, but not as much, very minimum. This is the most spectrum. Okay, right. It's pretty much like there are many foods on earth, but not many food that can make you happy. Some food can make you vomit, right? So you pick the food that makes you happiest the most. Right. Okay. So we kind of clamp here. You can open again. So you want to see here? Why is it pink? 2 color, blue plus red. You got pink. So in the sensor here, maybe you can ke belakang sikit. Yep. There are many 4 types of light in here. So you can use the light to trigger photosynthesis, or lights to trigger electron transport, or lights to clear chlorophyll from electrons. So there are many kind of lights. Okay. So you can clamp. You see the springy thing in the middle? That's the thermocouple. So thermocouple is used to measure temperature. So we clamp it, and then we look at the screen. So when we look at the screen, may tunjukkan screen ya. So this is the reading of the screen. So the screen is telling the current assimilation is adjusting, because we just open the chamber, we change the light, we change the CO2. So at the moment, minus 32, it means CO2 releasing is more than CO2 taken into the cell, right? So meaning that respiration is dominating, photosynthesis not dominating. But with the progression of time, because we have increased light and CO2, photosynthesis will dominate. The moment photosynthesis dominate, assimilation will become positive, like this. See, become positive now. What about the stomata conductance? GSW. G is the universal sign for conductance. S stands for stomata. W stands for water. Stomatal conductance to water, which is the, what color is that? Green. Green. And that is the measure of it. So it is positive. If it's positive, meaning that the stomata is actually opening. How do you know it's opening? Look at the green bit. It's going up, meaning that the stomata are opening. If it goes down, stomata are closing. If it's stable, stomata not kind of they are at equilibrium. On a piece of leaf, there are maybe 2 million of stomata. Not all stomata open and close at the same time. Some are closing, some are opening, some don't do anything at all until needed. Okay, so we call it at equilibrium if this becomes straight, the green line. Yeah, for the assimilation also it becomes straight as well. Right, let's do a little experiment. The light reading now is 1000. We set it at 1000, right? Will this photosynthesis increase if we give more light to it? So we can change it from 1000, maybe change it to 1200. Let's see whether the photosynthesis or not. So don't forget to water your plants. That's very crucial. Right. So we go back to the measurement tab. Pay attention to the purple line. It's going to take some time. I think this is a shade plant. If you are working with the real tropical plant, plants that are exposed to the sun, that's going to be more responsive. So we expect the photosynthesis to increase, but it's not increasing. It stays around 2. So that's actually a physiological phenomenon. Why is it? I've given you more light. Shouldn't you increase your photosynthesis? Yeah. So there are a number of physiological reasoning for that. Partly maybe some of the Rubisco activase is not yet activated. Yeah. Rubisco needs to get activated first before it can does the job. Yeah. Or maybe the light is already too much. Yeah, because this is a shade plant. And usually shade plant is actually around maximum 1000 micromole. The moment you give something beyond, it's going to cause what we call as photo inhibition or photo. Ya, seperti pergi ke pantai pakai sunblock. Kemudian lepas 3 jam jadi udang bakar. Ya, right. Okay, so ini cuma untuk Kelvin cycle. Okay. Macam mana pula kalau nak tahu photosystem, kesihatan photosystem? Itu kita boleh gunakan ini. Gunakan ini. Jadi ada 2 daun. Boleh turn on kan? Ini adalah fluorometer/porometer. Ada daun yang sudah light adapt, ada daun yang dark adapt. Kedua-dua ni akan bagi bacaan efisiensi photosystem yang berlainan. Mari kita lihat daun yang sudah di, cantiknya dia buat. Siapa buat ni? Sayang nak buka. Tolong buka kan? Ya, semangat artistiknya tinggi. Otomatik tak apa. Dua. Ini bagus. Student A ni. Kenapa kita bagi dia tutup dia? Okey, mari ambil. Basah. Lap dulu. Pasal dia transpirasi malam. Kadang bukan transpirasi, dia gutasi, guttation. Gutasi. Transpirasi airnya keluar ikut stomata. Gutasi airnya keluar ikut hydatod. Lubang lain. Okey. Mari kita tengok berapa bacaan fotosel. Daun ni sudah semalaman digelap. Boleh tengok berapa? 0.71. Okey. Okay, ingat ya bacaan itu. Jadi kita tengok yang sudah di light adapted di sekitar ini. Ya. Sepatutnya. Nampak tak berubah? Kerana daun yang sudah dark adapt itu bersedia untuk buat kerja sebab dia tidak bekerja lagi. Seperti baru masuk kerja pukul 8, kan gembira, kan tak stres, senyum, make upnya masih utuh lagi, kan. Ini sudah bekerja lama, kan. Jadi efisiensi sudah berkurang. Ini sudah kira sudah jam 3, kan. Yang ngantuk, gaduh-gaduhnya sudah 2 pinggan. Jadi keadaan itu boleh dibuktikan oleh mesin ini. Keberkesanan penggunaan cahayanya berapa. Sebab kita tidak tahu cahaya yang dapat sama-sama kan. Kita tidak tahu pokok ini guna atau enggak. Jadi dia boleh bagi tahu. Okey? Tetapi kita juga hendak tahu cahaya yang tiba di permukaan daun itu apa bacaannya. Boleh gunakan alat ini. Okay. Ini mari kita tengok. Ini luarnya, ini lampu warna apa? Putih kan? Putih kan? Betul ke putih? Dalam semua cahaya mesti ada satu warna dominan. Jadi mari kita lihat. Siapa nak buat? Tak cukup tangan. Nak pegang. Okey. Mungkin dekatkan sikit dengan sumber cahaya ni supaya dapat ini di bawah ini. Okey. Okay, tunggu sebentar, dia ambil warna cahayanya. Sudah keluar. Okey. Jadi, cuba lihat, itu cahaya putih itu sebenarnya jangan tertipu. Warna yang banyak di dalam itu sebenarnya dua warna, hijau juga biru. Dia beritahukan. Jadi ini adalah peta spektrum. Dia beritahu. Nisbah warna bermaksud kualiti cahaya. Ada cahaya merahnya berat, birunya kurang. Ada cahaya semua sama banyak. Contohnya cahaya matahari. Ini cahaya lampu kan. Kita tengok di luar ini, apa bacaan cahayanya? Kita tengok di ppfd. Jadi antara 400 ke 700 nanometer, itu bacaan cahayanya sekitar 6 mikromol. Sangat rendah. Kerana ini cahaya dalaman di kantor. Okay. Untuk warna biru sekitar 1 mikromol, warna hijaunya 3, warna merahnya 1. Jadi yang paling banyak di dalam warna pelangi itu warna hijau. Jadi lampu yang kita tengok ini dominannya sebenarnya warna hijau. Betul atau tidak? Ulang kembali ke sini, tengok kembali spektrumnya. Betul tak hijau paling tinggi? Tengok, hijau paling tinggi. Ya. Tenaga matahari macam mana? Mari tengok. Kau tak boleh ikut jauh. Oh, tak sampai. Kabelnya. Tolong ambil mataharinya. Tolong ambil matahari. Cahaya handphone selalunya biru. Selalunya biru yang berat.
Apa beza PS2 di sini?
Itu sebenarnya nak ada benda nak cakap tu sebab saya tengok file dia, cara dia kira lain dengan yang ini. Sikit ada yang tak sama, macam file dia ada FBFM tapi dia ni tidak ambil. Di dalam Excel-nya ada. Ya. Jadi adakah setting yang kurang betul? Mungkin dia tak upgrade. Tapi Excel-nya ada, tak apa, nanti boleh tengok. So untuk file PS tu kedua-duanya sama saja. Itu dia memang formulanya. 1 tolak Fs. Fs tu steady fluorescence dibahagikan dengan maximum fluorescence ketika lampu sudah light adapt. FM tu maksudnya maximum fluorescence, yang atas itu maksudnya light adapt.
Terus kalau ini kan kita pakainya langsung. Kalau di sini penggunaan seperti apa?
Yang ini
harus flash.
Dan ini pada flash juga. Ada flash. Ada flashnya. Flashnya di sini. Flashnya ada di fluorometry. Kejap. Aku lupa kat mana.
Beda versi.
Computation. Sekejap ya. Ni fluorometer options. Ini jenis pilihannya. Sekejap ya. Where's the result of fluorescence that we usually find? Kat sini. No, I think dekat, it should be. No, not that. Yes. Selalunya ini dia punya result. Dia punya kawalannya tu di sini. Measuring. Jadi flashnya itu di sini selalunya. Red target flashnya itu 10,000. Ini pun sebenarnya boleh pergi sampai 16,000. Ikut spesies pokok. Sekurang-kurangnya 8,000. Ini ada orang yang sudah tolong tadi. Cahaya matahari seperti tiada dominan, semua orang sama banyak. Kerana cahaya matahari itu datang dari luar bumi. Bukan dicipta manusia. Manusia tak mampu buat cahaya macam ni. Tak mampu. Ya, tinggi semua kan. Ya. Apa bacaannya pula? Mari tengok. Cukup tinggi, 1440. Ini kalau di sawah padi pukul 9-10 pagi dapatlah. Jadi tumbuhan yang hidup di dalam 1440 mikromol, tumbuhan itu akan menjadi tumbuhan suria. Sun plant. Okay. Alright. Okay. So cara ringkasnya itu saja. Adakah ini boleh buat? Ini pun boleh buat juga. Mari kita buat satu. Buka ni. Buka ni. Tadi kita gunakan fluorescence dengan alatan fluorometer. Alat ini pun boleh juga fluorescence. Ya, aku cakap campur aduk lah. Di Malaysia dia memang macam itu. Dia ADHD. Tak boleh nak fokus. Okay. Lapan. Besok dia perlu. Apa itu? Chlorophyll content kena guna alatan lain. Tapi ini pun boleh juga. Kesihatan klorofilnya boleh juga. Namanya chlorophyll A fluorescence. Boleh. Sedang nak dibuat. Jadi kesihatan klorofil boleh juga diukur dengan alat ini. Nama parameternya FV/FM. Sekejap ya. Buat. Okay. Kejap, tutup lampu dulu. Lampunya kena tutup dulu. Okay, lampunya kena tutup. Kemudian dia punya ini modulationnya on. Okay. Jadi daun ini sudah dibiar gelap semalaman. Jadi kita sekarang pergi ke fluoro optionsnya satu, semua betul. Mutation program. Ya. Ini sudah buka file belum? Dah. Okay. Sekarang ini kita nak lihat kesihatan chlorophyll A-nya. Kalau chlorophyll A-nya sihat, dia mampu tangkap cahaya sebanyak-banyaknya. Chlorophyll will be able to capture the most of light particles. So, at least must be able to capture 80% of the light particle given. The machine knows how much light does it give. And then the machine will measure how much the leaf has managed to capture. So we're going to see now. Bapak boleh ke sini supaya orang boleh nampak. Ataupun ini pusing. Ini pusing. Ini simpan. Yep. Right. Jadi itu bacaan. Cuba tengok berapa bacaan daun ini. Seperti yang saya katakan, sekurang-kurangnya 0.8. Bermaksud daripada misalnya 10,000 zarah cahaya yang diberikan, 8,000 ditangkap ke dalam chlorophyll A. Baru tangkap ya, belum guna. So macam mana kita nak tahu dia guna atau tidak? Itu kita pergi ke bahagian 2. Ya. Iaitu bahagian light adapted. Light adapted. Ini kena buka lampu lah. On. Tapi selalunya ambil masa sebenarnya. Tapi katalah kita guna. Tadi mana div yang nak guna? Ini kan? Ya. Ya, buka. Katakanlah ini daun yang sama. Sebab kita tidak ada masa lama untuk light adaptkan dia. Okay. Okay, mari kita tengok. Sebentar ya. Okay. Bagi dia stabil sekejap. Kemudian kita boleh tekan dia flash lagi untuk lihat efisiensi photosystem 2. Maksudnya tadi dia sudah tangkap 80%. Dari 80% ini, berapa pula digunakan untuk menjalankan photosystem? 8,000 zarah cahaya yang tumbuhan tangkap itu, bukan semua boleh guna untuk elektron transport. Ada sedikit yang akan terbuang kiri kanan. Okay. Selalunya kita tunggu sampai ini positif. Lights sekejap ya. Tak menyala ni. sudah on. Alah, kenapa 1,000 patutnya? Masalah teknikal. Okay. So, bagi sekejap, bagi dia naik sekurang-kurangnya dia positif. Jadi apa expectation untuk kita lihat? Sepatutnya bukan bacaannya 0.8, dia sepatutnya lebih kurang. Okey, sudah boleh kan? Jadi kita tengok sekarang. Kita jalankan sekali lagi untuk lihat bahagian ini, light adapted, maksudnya lampu sedang pasang. Berapa bacaannya? Unlockkan. Ya. Jadi ini bacaan sekarang. Jadi dia keluar semua itu. Jadi kecekapan fotosistem 2-nya adalah kira-kira kurang, sangat rendah kerana daun ni kita tidak light adapt betul-betul. Dia ada satu lagi ukurannya 5 CO2 untuk setiap unit CO2 yang untuk setiap unit cahaya yang ditangkap, berapa unit CO2 yang diasimilasi. Kecekapan 5 CO2. Jadi ada dua jenis kecekapan di sini. 5 PS2 beritahu kecekapan fotosistem. 5 CO2 beritahu kecekapan Kelvin cycle. Dengan menggunakan teknik fluorescence. Yang di permulaan tadi tidak guna fluorescence, kita guna gas exchange biasa saja. Jadi ini lebih dalam. Tak pasti pula, ini kalau orang weed science dia sukalah. Kalau ada produk herbicide untuk tahu mechanism of action. Kita nak tahu herbicide itu dia putuskan aliran elektron di mana. Ini boleh guna. Okay. Tapi ini selalu ceritanya panjang. Kena prep dulu. Alright. Okay. Okay. Itu sajalah kot demo. Ada soalan ke? Soalan lain ke? Saya ada sesi lain kat belakang. Moderatornya ada soalan. Sudah buka warung baru di belakang. Ya. Benih apa itu? Yang ini untuk lebar daun. Tapi untuk duit boleh. Duit kertas. Untuk ini kita gunakan alat, bukan alat ini. Dia alatan kamera fluorescence kamera. Kamera fluorescence kerana dia 3D. Ini satu lapis saja, 2D atas saja. Ini ada tepi kan, ada lonjongnya. Ya. Tapi untuk daun, untuk duit boleh. Untuk duit kita fluoresce juga waktu malam. Ya. Okey. Apa jadi? Moderator, tutup sekejap warung. Sini. Jadi itu sajalah untuk demonstrasi. Ada soalan ke macam mana?
Ya, baik. Mungkin dari Bapak Ibu ada yang ingin langsung ditanyakan, silakan Bapak Ibu. Penggunaan likor, apakah laju fotosintesis bisa diukur pada daun yang sudah dipotong?
Boleh. Caranya adalah, saya tunjuk. Caranya adalah, ambil pokok ini yang tinggi ni. Bawa ke sini. Saya tunjuk cara dia. Boleh? Bukan boleh, bisa. Caranya adalah, katalah pokok itu terlalu tinggi. Lakornya saja sudah 20 kilo, mau terbang macam mana ke atas kan? Jadi katalah daunnya tinggi, kita boleh potong bawa ke bawah, tapi kena cepat sikit. Ada gunting?
Enggak.
Tak ada tak apa.
Langsung potong aja.
Tisu. Air. Jadi boleh ambil, katakanlah daun yang hendak diukur itu ini. Jadi kita boleh ambil satu dahan ini, putuskan dahannya, masukkan daun tisu. So ambil tangan ini. Buang. Letak dalam vacuum. Jangan pasang. Kemudian cepat-cepat ikatkan. Kalau ada parafin lagi bagus. Ya. Jadi ini boleh tahan 30-40 minit. Jadi ambil ini. Boleh juga. Boleh. Ya dapat macam. Menjawab soalan kan? Soalan kan? Itu caranya. Boleh. Ada lagi soalan?
Apa? Apakah morfologi daun mempengaruhi efektivitas alat? Daun kecil, daun bergelombang, daun...
Daun yang beralun itu surface area-nya lebih tinggi. Jadi sinaran cahayanya akan kena lebih kepada banyak klorofil. Jadi lebih banyak klorofil, lebih banyak penampilan hasil, lebih lanjutkan recycle-nya. Oh, ada ni. Tak ingat. Morfologi daun memainkan peranan dan juga umur daun. Umur daun itu untuk fotosintesis jangan ambil daun yang terlalu muda. Ini caranya adalah bila kita lihat ini kan, cara nak pilih daun sangat penting. Yang paling hujung di pucuk ini jangan ambil. Ini bukan daun, ini primordia. Yang kedua ini daun tapi masih belum matang. Jadi kita ambil daun yang ketiga selepas itu. Nombor 3 sampai nombor 5. Jadi kalau 3 ini sudah nampak elok, boleh ambil. Kalau tak elok, pergi nombor 4. Nombor 4 ni sudah nampak sempurna, besar. Jadi ambil yang ini. Kenapa tak boleh ambil daun yang tua? Senescent. Bila senescent, klorofil sudah pecah. Jadi bacaan ini tidak betul. Jadi ada kesan. Kena pilih betul lah. Ya. Lagi.
Tadi daun yang dipotong katanya harus pakai, kenapa harus pakai tisu?
Tisu ada air.
Oh, ada air.
Ada air. Ya. Daun dengan mati dia segar 30-40 minit boleh.
Oh, harus dijaga kelembabannya gitu.
Iya.
Oke.
Pelepas sawit tak boleh guna tisu. Dia kena guna di Malaysia pun orang tanya soalan tu. Triknya adalah kena cari vials, masuk celup di dalam vials. Lepas itu letak sikit gula untuk kawal osmotic pressure dia, supaya air dari dalam daun tidak keluar. Air dalam daun saja, daripada luar saja masuk dalam. Bagilah daun. Saya tunjuk. Boleh. Semua pokok boleh buat. Semua pokok boleh buat. Kecuali pokok sayur. Janganlah sawi. Nak potong kenapa? Pergilah kat pokok tu. Sawi jangan dipotong. Kerana dia herba yang umur 4 minggu, 5 minggu. Sistem vaskularnya tak matang. Kalau kita potong, nanti dia jejaskan pressure dalam daun. Ini tak apa, ini sudah keras. Kan? Kalau kita potong pun okey. Okey. So, potong itu kalau pokok itu sama ada tinggi ataupun pokok itu sudah keras, okey. Kalau pokoknya masih muda, jangan. Okey, ada lagi?
Kalau silakan Pak Edi.
Ya, Pak Edi.
Ini aquatic plant. Aquatic plant. Ya, kita ukurnya ini dimasukkan ke situ atau
ada aquatic chamber. Aquatic plant ni apa itu? Teratai seroja.
Teratai.
Kalau teratai, setting mungkin kena tukar sikit sebab teratai stomatanya hyperstomatos. Kalau ini hypostomatos, hypo maksudnya stomatanya di bawah sahaja. Kalau teratai seroja, stomatanya di atas saja. Kena beritahu kepada mesin. Ini beritahu, nanti dia akan masukkan di dalam equation. Baru tepat. Jadi betulkan equationnya dan keringkan bahagian bawah itu juga. Jadi kena ambillah teratai itu. Kena ambil. Teratai tak apa tahu sebab dia susah layu. Ya, kerana di dalam filter itu ada lubang banyak, pores. Jadi boleh. Ya,
Baik, sudah cukup sepertinya, atau mungkin dari Bapak Ibu ada yang ingin ditanyakan langsung, silakan Bapak Ibu. Ayo.
Ya,
Berapa?
Ya. Yang ini 6.
Masing-masing beda. Apa ini perkalian?
Jadi betulkan lift area-nya boleh betul di sini. Constant. Sudah dia kejap. Ini sudah letih langsung ini.
Ini kena dibenarkan ini hibernasi dalam jadwal. Jika mungkin nomor kita jadi
Sudah. Sudah. Baik, mungkin karena waktunya juga sudah hampir 1,5 jam. Terima kasih Bapak Ibu yang telah mendengarkan pada kuliah pada pagi ini. Mungkin langsung saja ke sesi selanjutnya, yaitu penyerahan sertifikat yang akan disampaikan oleh Pak Edi, Prof. Edi kepada kami. Persilahkan Pak Edi.
Oke, terima kasih. Terima kasih Pak.
Baik, Bapak Ibu. Mungkin satu lagi souvenir. Dr. Nazmin bisa ke depan lagi, souvenir from our department ya.
Apa ini?
Yang kulit siapa gitu. Mungkin selanjutnya kepada perwakilan dari PT Unitama Analika. Ya, baik. Terima kasih kepada Prof. Edi yang telah menyampaikan sertifikat dan kenang-kenangan kepada pembicara dan perwakilan dari PT Unitama Analika Perkasa. Mungkin sudah di penghujung acara kita pada siang hari ini. Terima kasih kepada Bapak Ibu semuanya. Dan Pak Edi ada yang ingin disampaikan? Oh iya. Sekali lagi terima kasih kepada Bapak Ibu. Kalau ada pertanyaan mungkin bisa dilayangkan langsung ke Dr. Muhammad Nazmin Yapa dan juga Ya, kalau ingin tanya-tanya tentang likor, ada ataupun mungkin mau beli likor di institusinya, mungkin bisa langsung nanti kontak di Unitama Analitika Perkasa ya sebagai distributor likor di Indonesia. Mungkin itu saja. Terima kasih Bapak Ibu semua yang telah hadir di Zoom pada siang hari ini. Kami dari Departemen Agronomi dan Hortikultura mengucapkan terima kasih atas kesediaan Bapak Ibu semua dalam hadir dalam acara BIMTEK AGH ke-7. Mudah-mudahan bisa memberikan manfaat bagi kita semua, khususnya penelitian-penelitian yang mendukung penelitian-penelitian di bidang fisiologi. Saya sekaligus MC dan juga moderator undur diri. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh. Selamat siang semuanya.
Terima kasih banyak. Jadi visualnya siapa Pak? Visualnya iya, saya fisiologi.